Have you ever stopped to think about like those really huge language models? I mean, the ones that can just spit out text that sounds like a human wrote it.
Oh, yeah. It's pretty incredible what they can do now.
Yeah, and it's, mind-blowing almost. Like, how are they doing that? I mean, they can do so much, but if you try to like peek under the hood, figure out how they're doing it,
It's a bit of a black box.
total mystery, right?
Hmm.
There are these crazy complex black boxes. And you know what some of the recent research we've been looking at has been saying?
Hmm.
This whole lack of transparency thing, it isn't just some intellectual puzzle to solve. It could actually be kind of risky.
Oh, absolutely.
I mean, we're talking about systems that could do things we don't expect, right?
Right.
Maybe even like bad things.
Yep.
And we might not even know why.
That's a huge concern, right? As these models become more powerful, and I mean they're everywhere now.
Oh, yeah.
So figuring out how they work on the inside, it's not just a fun thing to do anymore. It's crucial if we want to develop them responsibly.
Yeah.
One of the biggest roadblocks, at least from what we've seen in the early research, is this thing called polysemanticity. It's kind of like imagine a single connection inside the model trying to represent like a ton of different ideas.
All at the same time.
Yeah, at the same time, totally unrelated ideas, right? Imagine like one word, but it has completely different meanings depending on how you use it. It's like, how do you even figure out what it really means in any given moment? That's what we're dealing with, but at the level of individual neurons in these massive LLMs.
So each neuron is firing off in response to all sorts of stuff that doesn't seem connected at all.
It-
Kind of like trying to read a language where every symbol has like a dozen different meanings all at once.
yeah, it's pretty wild.
It's a mess. So traditionally, people have been trying to make sense of all this using what they call post-hoc methods, like sparse autoencoders,
Right, right.
SAE.
Essays, yep.
But you know what resources are saying? Those methods, they could be super computationally expensive.
Definitely.
And we might only get like a little peek into what's really going on.
Yeah, it's like you're adding another layer of complexity
Right.
on top of something that's already insanely complex.
Exactly. So that's where this really cool new thing comes in, right? It's called MoE-X,
MoE-X, yeah.
which stands for Mixture of Experts Made Intrinsically Interpretable. It's a mouthful.
It is a bit of a mouthful.
But the basic idea, if I'm getting this right, is to basically build interpretability right into the architecture of the language model.
From the ground up, yeah.
So instead of getting all these tangled up concepts, they try to prevent it from happening in the first place.
Exactly. Instead of, trying to understand this black box after it's already built, you try to build it with parts that are, well, more transparent from the start.
Makes sense. So we've got this research paper we've been looking at, plus some extra materials that give some helpful background. And they all seem to agree that this approach it's a pretty big deal.
Yeah, it's a really interesting shift in thinking.
So for our deep dive today, let's try to figure out what is it that makes MoE-X so different? What are they doing that's new? And why is this potentially, such a big step towards AI that's actually understandable?
Sounds good to me.
Awesome. So let's the foundation, right? They built on this idea that wider and sparser networks, those are the key to figuring out interpretability.
Yeah, they started with a study using chess data, actually. Trained models similar to GPT-2 on basically records of chess games. So they're treating the moves as a kind of language.
Okay, so the model's learning to speak chess.
Exactly. And chess is actually like really helpful for studying this interpretability thing because the state of the board at any given point, it's like a clear ground truth.
You know exactly what's happening.
You know exactly what's going on. So they use something called the Board State Property Coverage Score, BSP coverage score for short. Think of it like how well the model's internal signals match up with, things that make sense on a chessboard, like where a certain piece is.
Okay, so they're checking to see if, say, a neuron fires when the black rook is on h8, something like that.
Exactly. So they started playing around with the structure of the model.
Okay.
And what they found was really interesting. They found that if they made the hidden layers in the MLP part of the network bigger, like wider,
Wider.
then the interpretability, as measured by that BSP coverage score, it went up.
Okay. So wider networks, more interpretable.
Yeah, and they also found that this thing called the hidden size multiplier, scaling, that was more effective than just like increasing foot dimension.
Huh.
And they also found that having sparser hidden activations, meaning fewer neurons firing at any given time, that also led to more interpretable neurons.
Okay, so sparsity makes sense, right? If fewer neurons are active, it's easier to figure out what they're actually doing. But why would making the network wider help with interpretability? That's a little counterintuitive.
So the idea is the wider the network, the more room the model has to dedicate neurons or groups of neurons to very specific things. If the network is too narrow, the model might have to cram multiple features onto a single neuron. And that's where the polysemanticity problem comes in.
Gotcha. So it's like having a bigger canvas to work with?
Right. And then sparsity comes in and helps reduce the interference between these specialized neurons.
Okay, I'm following you. So we want wider and sparser networks for better interpretability. But training a huge sparse network from the ground up, that sounds super computationally expensive.
Oh, absolutely.
So is that where the mixture of experts architecture comes in?
Exactly. That's where SMO, sparse mixture of experts, comes in. It's kind of a clever way to do both of those things. So instead of one massive MLP in each layer of the transformer network, you have a bunch of like smaller MLPs working in parallel. They call these experts.
Experts, okay.
Yeah, and then there's this other network called the gating network. It basically looks at the incoming word or token and decides which of those experts are the best ones to handle it.
So for each input, only a few of these experts actually get activated.
Exactly.
It's like having a team of specialists and you only call in the ones you need for the specific task. I like that.
Yeah, it's a really neat idea. And the cool thing is you can actually think of an SML layer as being equivalent to a single very wide MLP. Like the hidden dimension of that single MLP would be the sum of the hidden dimensions of all the individual experts.
Okay, so it gives you the width without having to train one massive network.
Yeah, and it's inherently sparse because only the active experts are doing anything. The neurons and the inactive experts, they're basically zeroed out.
Clever. But the research paper found out that regular MoE models, even though they have this width and sparsity, they aren't really designed for interpretability. Why not?
So there are a couple of reasons. First, even though the layer is sparse, each individual expert is still usually a dense MLP on the inside. So within each expert, you can still run into those polysemantic neurons, those tangled representations that make things hard to understand.
So it's like you solve the problem at one level, but then it pops up again at a different level.
Exactly. And then the second thing is the way that traditional MoE models choose which experts to use, it's mostly focused on making the model perform well, getting good accuracy, being efficient.
Right.
It doesn't necessarily pick experts that have like more interpretable activation patterns.
Okay, so MoE gives you the structure, the width, and the overall sparsity. But MoE-X is about fine-tuning the individual experts and how they're chosen to specifically boost interpretability.
Exactly.
Cool, so let's dig into those innovations.
Okay.
The first one is they use something called real U experts. What's so special about using the real U activation function?
So this might seem kind of simple, but it actually makes a big difference. They use the real U activation function, rectified linear unit, inside each expert instead of GOU, which is what a lot of large language models use.
Okay.
And they found that this makes the experts much more sparse. Real U basically outputs 0 for anything negative, so you end up with more neurons that are inactive.
Got it. So how does that make the whole model more interpretable?
Well, the more sparse the experts are, the more likely it is that the active neurons are focusing on very specific features. It helps to untangle the representations within each expert, which is what we want.
Right, so it's like each expert becomes more specialized.
Exactly. And they even did a test where they swapped real U out for GLU, and they saw a big increase in the number of active neurons, and the interpretability score went way down.
So real U really is crucial for keeping things sparse and interpretable. Okay, so that's the real U experts. The second big innovation is sparsity-aware routing. This sounds like it tackles that second limitation of regular MoE we were talking about.
Exactly. The goal here is to send each input, each token, to the experts that are most likely to have sparse activations. Ideally, you'd want to calculate the activation of every expert and then pick the sparsest one.
Makes sense.
But that would defeat the whole purpose of using MoE in the first place. It would be too computationally expensive. So what they did was come up with a way to estimate the sparsity of each expert's output without actually having to calculate it directly.
Hold on, so they're trying to predict how sparse the output will be before they even run it to the expert.
Exactly.
How's that even possible?
They make some smart assumptions about the encoder weights inside each expert. They basically treat the weights as if they were random numbers from a specific distribution. And using some statistical tricks, they can estimate the probability that each neuron have a positive activation. And remember, RealU only outputs positive values or 0.
So by looking at the properties of the weights and the input, they can guess how sparse the output is going to be.
Exactly.
That's really neat.
So the gating function looks at these estimates and picks the experts that are predicted to be the most sparse. And what's even more clever is that this whole process actually encourages the experts to become more sparse over time.
How so?
Because the model learns that if an expert tends to produce a sparse output, it's more likely to get picked. It's like a self-reinforcing cycle.
It's like they're being rewarded for being sparse.
Exactly.
That's some seriously cool design. Did all of this actually work in practice, though? How did they test it?
They went back to that chess gameplay dataset. They compared MoE-X to all kinds of different models, regular dense models, models with different activation, other MoE models. And the results, they were pretty impressive. MoE-X got the highest board reconstruction score, way better than the others, even while using the same number of parameters.
So for the same computational costs, MoE-X is much more interpretable.
Exactly. And they also tested how interpretability scaled as they made the models bigger. As they added more parameters, MoE-X got more interpretable much faster than the other models.
Cool. So the innovations are really working. What about the comparison to sparse autoencoders, the SAEs? Those are supposed to be the method for interpretability, right?
Right. So they compared MoE-X to a GPT-2 model that was augmented with an SAE. And MoE-X achieved a higher level of interpretability, even though they had roughly the same number of parameters overall.
But didn't you say earlier that SAEs can hurt performance?
Yeah, so that's the other big thing. MoE-X achieved this interpretability without any loss in performance. The SAE model actually had a noticeable drop in performance.
Makes sense because the SAE is kind of an afterthought. It's trying to interpret something that's already been built.
Exactly. Whereas MoE-X learns to be interpretable from the start.
Okay, and then there was that figure with the TSNE projections. What was that all about?
So that was showing what the different experts in the various Mo models were learning. And with MoE-X, the projections showed these really clear clusters of weights for each expert.
Like they were each specializing in different things.
Exactly. And this was much less clear in the regular Mo models. So MoE-X is really encouraging the specialization, which is great for interpretability.
Awesome. So the chess experiments look fantastic. But chess is pretty structured, right? It's a relatively simple world.
Yeah.
How did MoE-X do with natural language? That's way more complex.
So they trained small and medium-sized MoE-X models on a ton of web data, and then they tested them on standard language modeling benchmarks. They used something called perplexity to measure performance.
Okay.
But for interpretability, they did something really interesting. They actually used other large language models to try and interpret the activations of the MoE-X models, and then they scored how accurate those interpretations were.
Wait, so they used LLMs to understand LLMs? That's pretty meta.
Yeah, it is.
And how did it go?
So the Mo models, including MoE-X, they did better than the regular GPT-2 models in terms of perplexity, so they're good language models.
Okay, good.
And for interpretability, the small MoE-X model did about as well as the GPT-2 model with an SAE, and the medium MoE-X actually did better.
Nice. And again, the SAE model had that performance hit.
Yeah.
So MoE-X wins on both counts.
Yeah, it seems like it.
And they even showed some examples of the kinds of concepts that different MoE-X experts were learning, right?
Yeah, they showed that one expert seemed to be focusing on the word against in sports context. Another one learned about celestial objects, Roman numerals, things like that.
So they're learning these meaningful, coherent concepts. Very cool.
Yeah, it's pretty compelling evidence that MoE-X is doing what it's supposed to.
Absolutely. So it really comes down to those two innovations, RealU experts and the sparsity-aware routing. And when they did those ablation studies, taking those things out really hurt both sparsity and interpretability.
Exactly.
So to sum it all up, MoE-X is a brand new way to design language models. It's not just about being good at generating text, it's about being understandable.
Right.
It uses WIP and sparsity from mixture of experts, and then adds those two special ingredients, the RealU activation and the sparsity-aware routing. And together, that seems to make a big difference.
Yeah, it's a really elegant approach, and it seems like a much better alternative to relying on those computationally expensive post-hoc methods.
Like the SAEs.
Exactly.
And the impact of this, I mean, think about areas like healthcare and education. These are fields where trust and transparency are super important.
Absolutely.
If we can build AI that we can actually understand, that could be huge.
I think so too.
It's really exciting. So thinking about MoE-X, I'm wondering what other kinds of architectural innovations might we see in the future? What else can we do to make AI more interpretable? And how will all of this change how we interact with AI, especially as it becomes even more integrated into our lives?
Those are great questions.
Yeah, it's something to think about. If you want to learn more about the technical details, definitely check out the research paper and the supplementary notes. MoE-X is a really promising step in the right direction,
It is.
and it'll be interesting to see where it goes from here.